So before we get started, let's just remind ourselves there's going to be no class tomorrow. I would hope you use that time to work on this sort of low stakes quiz and extra credit. That's all done on Canvas. You're not scanning anything. Everything's going to be answered and done on Canvas. And then instead of us meeting on Tuesday, you can work on your midterm. I will post the midterm Monday night. You need to write up your solutions, scan and upload them by 4 p.m. on Wednesday. I don't know yet. I didn't finish it. Probably between 7 and 10. But you know, the question was how many questions will be on the test. I haven't finalized it yet, but you can imagine somewhere between 7 and 10, and they all have different parts. I mean, it's kind of hard. You know, I have to make a test, and then I have to sort of pretend to take it myself to see how long it takes me, and then I decide if it's fair for you. All right, so there we go. So we're going to have a practice test on Canvas tomorrow. We'll have the real test next week, and that's that. So good stuff. Oh, yeah, we will have class back in action next week on Thursday. So I'm assuming you guys all have exams and stuff next week, I would imagine. So figure give you a break from, you know, if we're giving you a take-home test, normally you take a test in the classroom, but since it's take-home, we're not going to make you come in. Now, that being said, if you have questions, you got to email me and let me know. And we can either Zoom or I don't think they want us to meet in person. I don't know the real rules, but I'm happy to Zoom. And I can pretty much Zoom any time of day, provided I'm at my house and not, you know, hanging out somewhere. Anyhow, feel free to do that. Don't be shy. All right, so we need to do some math. So let's summarize what we've done this semester. Because this is going to be important for understanding what you should know how to do for the test. So the first thing we did is we did applications. So applications of the integral. In particular, the integral of f of x from a to b. And let's remind you what these things you should know how to do are. You should know area. You should know volumes. You should know arc length. You should know surface area. And the last thing we did was we did hydrostatic force. So that was also something we did that was an application. And then some other applications well, I guess we can put it this way. We can also say, so linear motion. And just to remind you of what that means, we talked about that briefly. That was things like acceleration, velocity. And how those relate to integrals. I'm not going to go through that. We did one of those was on the first homework, I believe. That's really a topic from Calculus 1, but it technically, those ideas are fair game for anything I can ask you. Does anybody have any questions about this? All right. So that was a big chunk of the term so far, applications of the integral. what else was a big chunk of the term was techniques for computing the integral. Both the definite and the indefinite integral. So what should you be responsible for? What should you know how to do? Well, you should know how to do the basic formulas. And I'm not going to write any of these down, but what I'm saying is you should know how to do in basic ones, polynomials, exponential, logarithm. You should know the basic formulas, sines and cosines. And then you should understand substitution. You should understand how to employ parts. You should understand trig substitution. Those ones were probably the most difficult. You should understand how to do partial fractions. And then, of course, you should also know, which we just recently did, numerical integration. And I'd like to point out what's the difference between all of these. The first 5, all these result in exact values and or formulas. This one down here, numerical integration, one of the key things to keep in mind is this only provides approximate values. So it's important you understand the distinction. Does anybody have a comment or a question on any of this? Now remember, this is not a time test, so you don't need to stress yourself about memorizing things. It's not the point. You should concentrate on understanding how to do these things. Not so much that you suffer through the trig substitution or you suffer through the partial fractions, but you understand how it works and what's correct strategy and what is incorrect strategy. So you might think to yourself, okay, so this is the kind of stuff he's going to ask me, integrate some functions or do some of these applications. And I can, but I can also ask you more in-depth questions on sort of, can you do a problem that is not just a direct procedure? Can you? Can you apply knowledge of some of these formulas, or can you apply knowledge of the definition of the integral to obtain information or obtain a result? So yeah, you're most likely to see problems that fall under one of these two categories, but it is possible that you see a problem that might not look like it's under these categories, but it is if you just interpret it correctly. All right. Any questions or comments on these two things? Okay, then, so that leads us then to sort of our sort of last topic before we take this test. And it turns out to be one that is of theoretical and also practical importance. And so let's ask ourselves, so what now? The first thing we need to understand is that we didn't cover everything there is to say about integration. And in fact, there's a lot more that could be said about integration, applications, and how to compute integrals. And a lot of that is saved for other classes because there's only so much we can cover in this class. And don't forget, too, another thing to keep in mind is that you know, I've said this before, this kind of upsets people, but in many ways, calculus is an introductory mathematics course. It's what it is. So it's this is an introduction to higher many types, branches of higher mathematics is a better way of saying it. And also the mathematics that you need in many other of the natural sciences and social sciences. So we can't cover everything there is to learn. And really, I always like to think of it this way. What you are capable of integrating now, if this classroom that we're in is like, if it's filled with all the integrals that we can think of, you know, maybe like a small corner of a 10 by 10 of this room is what we know how to actually do. So, okay. All right, so switching colors here. So in many applications, such as probability, finance, engineering, CS, etc. We must integrate not over an integral, or excuse me, an interval, but over all values. Or another way of saying that that's probably a little more correct, but over the real values or the real numbers. Now, right now, I'm not going to get into any of these applications, but many of you are already familiar with one, even though they don't tell you this. If you've ever taken an elementary prob and stats course, have you ever taken one, Shobit? I'm sure many of you have, whether in high school or in college. And what happens in one of these courses is you spend a lot of time looking up tables in the back of your book, looking at, they call them Z values. And if I can sort of share a page here with you. Perhaps some of these images look familiar to some of you. Maybe you spent time in a Prob and Stats course looking at a table like this or plugging numbers in. And it's often not very clear what you're doing. And that's one of the unfortunate things about teaching probability and statistics to students who have never seen calculus. What these values represent is they represent the area under a certain curve. And if you look at this sheet, you'll see that there's like this bell-shaped curve, and then they have this purple region here. And what these numbers represent is they represent the area of some purple region. And so in one of the basic things in probability and statistics, when we're doing what's called the standard normal distribution, we need to know the area under a curve. And we're not just calculating it from, say, 1 to 2 or 0 to 5. Oftentimes, we have to calculate over all real numbers. So what am I really saying? Well, I'm saying this. So this creates a problem. Because this thing which we call the definite integral, this only makes sense if, first off, f is bounded on a comma b. Notice and this is a subtlety most students don't get in calculus yet. Notice the interval has to be a comma b inclusive. It has to include a and b. Remember, in previous classes, you may have talked about open and closed intervals. It's important to understand that you don't define an integral on an open interval. It must be defined on a closed interval. And number two, and this is what I'm more to the point, a comma b is a closed interval. Now, of course, you might say, well, why does that have to be the case? And what I'd remind you that the definition of the integral starts with this. So note, we define delta x as b minus a over n. This is the first thing we do when we're computing an integral, particularly defining it. So if I can't create this delta x, then the integral doesn't make any sense. So what we'd like to do is the following. So let's consider f of x equals, let's say, 1 over x squared. And let's consider it on 1 comma a. And the only thing I'm going to require of a is that a is greater. Actually, I'll use b to be consistent with what we used before. The only thing I'm going to require of b is that it's a number that's bigger than 1. So it might be useful to remember what the graph of this looks like. So let's say that this is the point 1. We'll change this and put this 1. This is 1. And then 2. So we go through this. And so what's the graph of this look like? If we draw it on this particular interval, it's going to sort of, I guess I should clean it up. It was a bad drawing. So we know there's this asymptote here. We know that the limit as x goes to infinity of 1 over x squared. We learn about this in Calc 1. We know this is 0. This is the point 1 comma 1. This is the point 2 comma 1/4. This is the point 3 comma 1/9, etc. And then, of course, way out here somewhere, you have the point b comma 1 over b squared, whatever b happens to be. And so one of the things we might ask is there some sort of way of assigning size to this? Like, is there an area here? So does anybody have a question? Someone has a question. No, I'm sorry, Eric, I missed your question. The practice test will probably be due sometime tomorrow. I don't know what time, 4 o'clock, midnight. If you need longer than 4 o'clock, you can have it. We'll just make it midnight for everybody. How's that sound? Shouldn't take you long, though. Midnight works. Okay, so here's what we'd like to know. So let's compute the integral from 1 to b. And I'm going to write it as x to the minus 2 because it's a little easier for me. And then I'm going to add 1. So this becomes x to the negative 1 divided by negative 1. And that's from 1 to b. And if I plug these things in, I'm left with negative 1 over b plus 1, which I'm going to rewrite as 1 minus 1 over b. So sometimes what happens here is you guys get a little confused because there's a b. Replace b with the number 2 and then replace it with 5. And you're going to see that there's a very simple pattern here. So if we're doing some investigation and we say, okay, we know that graph definitely has an asymptote. Its limit is 0 at infinity. And then we say, okay, is there some sort of way we can assign area to that red region? Of course, you might say intuitively, well, that doesn't make sense to you because that region is sort of infinite. So there's sort of like a counterintuitive thing happening here, but you have to think about what's going to happen now. So if I go to the next page, we might ask ourselves, what happens if b goes off to infinity? Well, let's look at it. Let's make a table. If I make a table of values, we'll call this guy b, and then the next column we'll do the integral from 1 to b of 1 over x squared dx. So we had a simple formula. So let's say if b is 10. Well, if b is 10, the integral from 1 to 10, we get 1 minus 1/10, right? But that's the same thing as 10 over 10. So you could, you know, if you want to get a simpler even formula for this, you could say, okay, let's rewrite this. This is the same thing as b minus 1 over b. Find a common denominator, which is b. You get b minus 1 over b. Now what that does is that allows you to pretty quickly create this table, so you get 9/10, which of course is 0.9, right? What if you do 100? If you do 100, then you get 99 over 100, which is 0.99. If you do 1,000, you get 999 over 1,000. Equals 0.999. And the fact of the matter is, as b is going to infinity, it seems to us that this number is going to 1. Does anybody have a question about this table? Now, what's nice is we can actually even verify this using our limit laws. So if we do this little experiment, we can verify this table because the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx, which another way of writing this, we already found out what this is. This is the same thing as this limit. We know this type of limit from Calc 1. This is just 1 minus 0, which is 1. So what this example does is it's motivating an idea. It's saying, okay, at least in this particular integral, if we let the upper bound of the integral go off to infinity, we have a limit. And that's promising because what that tells us is it tells us that there might be a way that we can modify our integrals to allow us to integrate over not just a closed interval a comma b, but an unbounded interval. So let's summarize what this sort of is telling us we can do. Yeah, I'm sorry. Is that green? Can you guys read that? It seems like it's, for at least for me, because maybe it's because I'm on an angle, it looks kind of like it's hard to interpret. Good. All right. So this example suggests that we can make the following. So it suggests we can integrate over a comma infinity if we make the following definition. The integral from a to infinity. So I'm taking away a number and I'm putting infinity there. What does this mean? What does this new symbol mean? It means the following. It means the limit as b approaches infinity of the integral from a to b of f of x dx. So if you think about the order of operations here, it's saying the first thing you do is integrate, and then you take a limit. So what we do is we give this a name. So we call this an improper integral. Questions, comments about this? Scary, huh? It's very important, though. There are many, many applications that require us to integrate over a region like this. And I gave you one very important one, which is in probability statistics. This is extremely important. Now, we're not just creating some definition just to create one. I mean, it agrees with our intuition, which is nice. That's another thing the previous examples is supposed to help illustrate to you, is that if we're going to make a definition for what this should mean, it should agree with, you know, what we've done in the past, and it definitely does that. So there's some terminology that you kind of got to learn to use with this. So if the limit exists, and is finite, so that means it's a number, we say the improper integral converges. And then if it doesn't converge, the word we use is we say it diverges. So the word converge and diverge are words you're going to be using the rest of this semester in this class. So you might as well get used to saying them now. Converge means a limit exists. Diverge means the limit doesn't exist. All right, let's do some examples of some. Oh yeah. You good? I'll go to the next one. Previous or this one? Very good. So let's look at two scenarios here. Let's check this out. Two basic ones that you can understand the difference between a converging one and a diverging one. So if I wanted to compute the integral from, say, 0 to infinity of e to the negative x dx, by definition, this is defined as the limit as b goes to infinity of this integral, 0 to b, e to the negative x dx, which is now, the integral is an elementary integral. You integrate this, it's minus e to the negative x from 0 to b. And this is, if I'm very careful with this, when I plug in b, I get minus e to the negative b. And then when I plug in 0, I get minus, so this is plus e to the 0. But this limit is just 1. The limit of e to the negative b, and maybe I should write this the other way so it's more clear what's happening. Maybe this will help illustrate to you. E to the negative b, that's the same thing as 1 over e to the power b. And the point that I'm trying to make is that this guy goes to 0. And of course, e to the 0 is just equal to 1. So that's the point. So you need to pay attention to this example because this is the correct way to do it. There are many incorrect ways to write this. This is a correct way. I noticed that there is a limit in front of each one of my expressions until I actually take the limit. That is the proper way of writing this. All right, now let's look at an example where it doesn't converge. Before I switch pages, we good? Does anybody have a question about this? Any chat? No? All right, let's look at a sort of non-example. So for this one, let's look at the integral from, say, 1 to infinity of 1 over x dx. The integral here, and by definition, this is equal to the limit as b goes to infinity of this integral. But the integral of 1 over x is the natural log. And so this limit is, the limit as b goes to infinity of the log of b minus the log of 1. Now, the observation and the thing to note here is even though the natural log of 1 is 0, this guy right here, this limit goes to infinity. So this limit itself equals infinity. So let me just emphasize it. Since the limit as b goes to infinity of the log of b is equal to infinity, the integral diverges. Anybody have a question about this? So while you're thinking, if you might have a question, I will remind you that traditionally, this is a topic that for some reason is just a difficult one for Calculus 2 students to grasp. This concept of what we call improper integrals. Previous slide. So again, this topic is often quite difficult because it's requiring a couple things. Not only that you can integrate, but that you understand this limiting process that's involved. So this is a, an in-depth sort of thing, but again, I repeat, it's one that pops up in many places. And so we got to be able to do it. Now, here's a cool fact that's worth remembering, and you should even try to derive it for yourself. So it's not just cool, it's also useful. The integral from 1 to infinity of 1 over x to the power p dx. So this guy has two things. It equals 1 over 1 minus p, excuse me, p minus 1. So it equals 1 over p minus 1 if p is greater than 1, and it's infinite if p is less than or equal to 1. So this fact is very useful. We'll actually use this fact later on in the semester. We already showed it, we've already showed this is true for p equal 2. We did p equal 2. We showed you that this is equal to 1 over 2 minus 1, which is, of course, 1. Oh, yeah. I thought you were done with that one. No. Oh, well, I thought you said you were done. Oh, my Lord. Yeah, you just got to yell at me. I thought you got to say, go back. I'm happy to go back. All right, good. All right, so this is something you might want to think about. Can you even verify it? I mean, it's not, you can actually do it for just write p everywhere and it works, but that's usually something we struggle with at first. Okay, so there's other types of improper integrals too. So it's worth mentioning these things. Earlier we did a to infinity, but you can just as easily imagine that we go the other way. Let's say integrate from negative infinity to b, and then the analogous thing would be, okay, I'll take my limit as a approaches negative infinity and integrate from a to b. And then you can actually integrate the whole party from negative infinity to infinity. And then what happens though is this has to be done using two integrals. So one way that we would do this is we might integrate, I'm not going to write the limit out. I'll just show you how to do it. The one way to do this is to just break the integral into two pieces. And the way you can think about this is you can integrate from negative infinity to c plus the integral from c to infinity. And this is true for any value c. So a common value that we would choose is 0. So it's often useful to set c equal to 0. again, I wouldn't try to memorize these things. What I would do is just look at the practice problems that I assign, look at the ones in the book, try to do them. And then the best way to learn this is really is to work on problems and refer to your resources when you're working on them. And a good way to gauge if you're getting it is how often do you have to look at the resources. Once you start doing examples without checking the steps and looking up what to do, then you have a good understanding of it. You're not going to learn this in 20 minutes. I mean, I know some of you think that magic's going to happen. It's just not. Calculus requires lots of hours outside of class. I know you hate to hear that. But I don't have a better answer for you. Okay, so there's also another type of improper integral that we'll just talk about briefly. It doesn't pop up as much as the one we just talked about. So another type occurs if f is unbounded. At, say, A or B. So let's assume f is unbounded at A. So remember what that would look like. So what that looks like is something like this. So let's say this is the point A. If it's unbounded, that means we have sort of like this asymptote, but now it's a vertical asymptote. So imagine we have something like this. So what we can't define an integral as normal, so we have to come up with a new definition. So we define the improper integral the integral from A to B can no longer make sense. So the way we make it make sense is we take a limit. And instead of approaching 0, what we have to do is we have to approach the value A. So we might pick a new letter. How about we pick, I don't know, we'll pick T. And so we have to take the limit as T approaches A from the right. Again, if it's unbounded at A, that means that f of A doesn't exist. So the definition of the integral doesn't make any sense. So we modify it like this. We modify it. So let's look at an example. Let's integrate from 0 to 1 over the square root of x. So we know that the function's undefined. it's 0. You can't plug 0 into that function. So this is not a traditional integral. So the correct way to do this is to take the limit as, say, t goes to 0 from the right of the integral from t to 1. And let's rewrite this. This is x to the negative 1/2 dx. So how do I integrate? I add 1 and divide by the new power. So adding 1 to negative 1/2 is the same as x to the plus 1/2. So this becomes 2x to the 1/2, evaluated from t to 1. And so if I rewrite this in a more familiar way, this is 2 times 1 minus 2 times the square root of t. And as t goes to 0, I get 2 minus 2 square roots of 0, which is 2. And so the improper integral converges. Yeah.
So how do you know that if you plug in 0, it will work?
How do I know if I plug in 0?
Yeah.
Well, I mean, we learned back in Calc 1, how do you take limits? What's the, you know, what do the limit laws tell us? If you talking about this step right here,
I know.
up here,
Yes,
how do I know to take the limit at 0?
yeah.
How did I know 0? Because this thing's undefined at 0. So I have, that's a good question. So the question is, how do I know to take the limit at 0, particularly from the right? Well, what am I integrating over? I'm integrating from 0 to 1. And this function is defined at every point except 0. It's not defined there. So that means it's going to have an asymptote. It's going to be unbounded. If you know, another way to think about it is to look at the graph. If I go to Desmos, if I go to graph this thing, y equals 1 divided by the square root of x, you're going to see that it has this it's unbounded there. And of course, I'm only interested 0 less than x less than 1. I'm only interested in this point, this particular portion of it right here. But a cool interpretation of this is saying that if I wanted to, this red region, albeit it's technically infinite, the fact of the matter is we can think of it as finite because that asymptote is approaching the graph is approaching its asymptote at a certain rate. So a way to think about this is if you had this infinite sort of red region, you would only need a finite amount of paint to paint it. Whereas if something doesn't get there fast enough, let's look at the one example we did otherwise. So earlier we did these two functions. Here's a good way to think about this. Earlier we did 1 divided by x squared. And we did it from, we were only interested in the points. We were only interested in this from 1 on, right? So that was the only piece we were interested in. So if I can if I just make this look pretty with a little, we found that this, believe it or not, what we found is we found that this blue region, even though it's infinite, we can think of it as having an area of 1 because that integral was 1. Now, what I'd like to consider is we also showed this guy diverged 1 over x. And we showed that the integral from, I guess I can put equal to there. The thing to notice is the green line, or excuse me, the green curve. The green curve is definitely going to 0. It has an asymptote. But the speed at which it's getting there how long it's actually taking it to get close to zero is much slower than the blue. And so another thing these improper integrals are doing is they're giving us a way to measure how quickly, say, a curve gets to its asymptote. And that actually turns out to be very useful in things like in computer science when we're doing, we want to know how long an algorithm is going to take to run, how many steps a certain algorithm requires. And so with these improper integrals, the fact that we can think of this blue region as having finite area, but we can also think of this green region as having infinite area, because it is infinite area, but it doesn't, you would never be able to paint it, because does that sort of, it's kind of like a weird thing to think about. And again, this stuff is difficult. It's hard to make sense of this in an hour-long class, in a 45-minute class, or an hour-and-a-half class. What you really got to do is you spend a lot of time thinking about this and pondering why. What I'm really saying is, I'm saying we can think of this blue area as finite, even though it's not. We know it's infinite technically, but we would be able to paint it and no one would know that we missed the tail of it. However, this green area, we would never be able to paint it because its area, the integral, is unbounded. Now you're going to say, well, that doesn't make any sense. And I've been telling you guys forever that, yeah, it does if you really think about it. A similar game, we're really playing with infinity here. And there's such a connection between, think of it this, there's no such thing as the smallest positive number. It just doesn't exist. Every time you have the smallest positive number, I cut your number in half and I'm closer to zero than you are. And we could go back and forth forever, and guess what we never do? We never get to zero, right? But if I take a sheet of paper and keep ripping it in half, eventually it is so small I can no longer rip it in half. So in that sense, in that interpretation, that paper eventually becomes so small I've gotten to zero, it's gone. But in terms of numbers, it doesn't. And that's the same thing that's happening here. This green region never ends. Now, technically, this blue region never ends either, but the curve gets so close to the x-axis so rapidly that we can ignore all that other stuff because it's so small relative to everything else. Just like eventually, if I keep ripping that paper, it's so small relative to my fingers, it no longer exists. Remember the other game that's also very much similar to this argument. When we were in Calc 1, like the first day of class, I said, okay, stand 1 foot from the wall. Now cut your distance in half, and then cut your distance in half. And then eventually you hit the wall. But if you play the game legally, you never hit the wall, because if you keep cutting your distance in half, you're never going to touch the wall. But what happens is we know it. Eventually, the distance between me and the wall is so small that it is physically impossible for me to actually go half the distance. And so I'm hitting the wall. It's crazy, ain't it? That's why I love calculus. Yes, question.
So how do you know that? How can you find the difference?
What do you mean, how do I find the difference? I did.
How can you know without calculating? Or do you have to calculate?
Well, you have to calculate the integrals. So I think the question you're asking is, how do I know why the blue one is finite and the green one's not? Is that okay? So the question is, why is the green region infinite but the blue region is infinite but not infinite? Well, that goes back to us calculating these things. If we go back, we showed this is the green region right here. The area of the green region goes off to infinity because that's 1 over x. But the blue region was 1 over x squared, and this integral, as we saw, goes to 1. It's really wild. This is one of those things. It's like, And there's this awesome example, which I would ask you to go ponder and read about. It has a Wikipedia page and has all kinds of resources. If you really want to blow your mind, how about this one? So there's this thing called Gabriel's horn, which is a certain solid And the crazy thing about this is its surface area is infinite, but its volume is finite. It's really, really wild. And there's a lot of stuff written about it, and it's a very cool learning experience. It's wild. Gabriel's home. And there's been lots written about it. There's lots of cool videos you can check out. I encourage you to do that. Anyhow, that was fun. It's overwhelming. All right, does anybody have a question? Because this is it for the midterm, then we go on to new stuff. Let me remind you, no class tomorrow. What's that? Yeah, improper integrals will be. I'm going to give you a homework with a few of them. You'll see they're actually not that bad. If you have a question, I'll answer them for you. Well, let me put it this way. They're fair game for the midterm. Will they be on there? I don't know yet. But this is fair game. And if you have questions, all you have to do is don't hesitate. What you do is you send me an email. And then I can answer it. We can Zoom, whatever you want to do. We'll figure it out. So I will see you guys on Thursday. Oh, someone's asked a question. Say it with my chest. Very good. I will see you guys Thursday. Please tell your friends, spread the word. There's no class, but don't forget you have your quiz tomorrow and the midterm Monday, Tuesday, and Wednesday. Well, it ain't gonna. You can use all 3 days, but I'm not gonna. It's not gonna take you that long unless you wanted to. All right, everybody. Thank you very much. I will talk to you all Thursday, if not sooner. Have a good weekend. Good luck on your midterms. Thank you.